Oh, hi. These set of questions are taken from possibly the hardest circuits exam I have ever encountered. These problems aren't impossible, there's just a lot of them, and 2 of them are very tricky. I want to help you out and show you how to deal with a superposition problem and a dependent source problem so that you can dominate the exam. So here's our circuit, and essentially the idea is that all of these sources, V1, V2, I1, are somehow contributing to the voltage across R3, which has 1K ohms. This dependent source is dependent on the voltage across this resistor. So we want to find that voltage. I think of this as some sort of constraints, extra constraints in our circuit analysis. So that's the idea, and that's how we're going to approach this. Essentially, the problem asks us to draw a circuit schematic for every independent source, which means that if we're going to do V1, we have to turn V2 and I1 off, and you'll see that. But we cannot turn off the dependent source. No. We have to keep that on for every independent source, and I'll show you how that works. We have to do it that way, or else we're not going to get the correct answer. So I'm going to draw the V1 circuit, and this whole section is worth 5 points. So here is our circuit. We turned off V2 by shorting it. That's how you do it for a voltage source. For a current source, you open the circuit. You still have your dependent source on, and the dependent source is now dependent on VX-V1. VX-V1 just means that the contribution to VX due to source V1, which is our voltage source. And that's all it means. This dependent source is still dependent on the voltage across this resistor. Now we just need to find some sort of expression for Vx, V1, some sort of expression to get us what that voltage should be. The idea here is that you're going to have your Vx, V1, and you're going to have some like iterations of Vx, V1, and it's going to equal to some constant. And that constant is determined by the source. That's what we're looking for. Don't forget to ground it. So one thing I can do, is I can like just look at this guy right here, and I see something that's easy. So we have 3Vx V1 is equal to Vx V1. We can write that because, KVL, and that's what that is. That's what that is. Plus VR4. Now, what is VR4? Here's VR4. To get VR4, it's just a voltage divider. Boom, 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 boom. So with that, I can evaluate this. We know R4, we know R3. And so when I do that, we have a problem. So here's the big problem. This is a problem that probably will stop you right in your tracks. So you can see the problem, right? That expression itself cannot be true. That cannot be true. If it were true, that would mean the trivial solution, Vx V1 equals 0. For this expression to be true, Vx V1 has to be 0. But really? Can it really be 0? Is there no contribution from this voltage source to this resistor? Really? Are you sure about that? Really? So how about this? I'm going to redraw this circuit. I'm going to redraw it so you can see it a different way. So here's the circuit. This is the same circuit as this. So from this, it kind of is more clear. And here's what I mean. The current flows from a high potential to a lower potential. That's how current flows. But for these guys right here, there's only one potential from this and this. R3 isn't getting anything from V1. At least that's what it looks like. And it turns out that's actually the case. It's not getting anything. So we can say this is true. Whoa. And it is true. It's true. I built this circuit in Spice, and yep, it doesn't give anything. It's 0. Time for our V2 circuit. And everything associated with the V2 circuit, even the answer, is worth 5 points, just like the previous. So here's my equivalent circuit. Now we have V1 turned off this time and I1 turned off still. And now we have Vx, V2. So this is the contribution of Vx due to V2 because this is a superposition problem. So now what we're trying to do is we're trying what Vx, V2 is. Vx, V1, we already found out it's 0. Yes, even though you expect something to be added for the previous circuit, we didn't have anything. Now, maybe we'll have, we're probably gonna have something because look, it's right there. This has to be contributing here some way, right? So this circuit right here is like, this circuit, it's like, I want to draw something that looks easier on the eyes. So here is our equivalent circuit. Now, these are the same circuits. Oh wait, I forgot to do this. Are equivalent, nice. To do this, I'm just going to do mesh analysis. So I wrote the two loops. We have I1, I2. And then I wrote the corresponding mesh equations for that. And we know, I1 times R5, which is, R5, that's R5. And, we have that. And, this contributes to that. And this is equal to V2. That makes sense. It's basically KVL, but with mesh analysis. Here, the same thing, that's what's happening. We got the voltages adding, and they would equal to 3 Vx V2. This is KVL as well, basically. Mesh analysis is KVL. What to do? So now we have this. We have our first equation, second equation. Now we're trying to get a third equation. So here's the other relationship. We have I2 is equal to R3 equal to Vx V2. Because if I2 is multiplying on R3, we're going to get Vx V2, and that makes sense. So if I write this as I2 times R3 minus 3 Vx V2 is equal to 0, and that is our third equation. Nice. So now we have our three equations, and we have our three unknowns. Our unknowns are I1 equals, who knows, I2 equals, and we have Vx V2. So we want to find this. So I set up the matrix, and so I solve for them using MATLAB or whatever calculator you have, and here's what I got. I'm like, what? What? Are you joking me? Like, are you serious? No way. No, I don't believe that. How can I believe this? I can't believe that. It's 0 as well. That actually kind of does make sense. If you do KVL around here, well, it's the same thing as you did before. It would just be this expression as well, and we know it would be 0. But that's strange, though. I can't believe that. So here's the deal. I want to redraw the circuit another way. I drew the circuit another way. This circuit is the same circuit as this. I didn't draw the R equivalent. I don't need to. So let's do mesh analysis again. I1 and I2. So what I did is this here is the first mesh equation. This here is the second mesh equation. So to find the third equation for our third unknown, we know that V2 minus 3 Vx V2 divided by R5 is equal to I1. So we have I1. Gives us this relationship. So here's our third equation. 3 equations, 3 unknowns. So what do we get this time? Here's what we get. Wow. Like, if we look at the circuit from this point of view, there's some activity going on. So if I look at like R3, we have I1 going into R3. We also have I2 going into R3, but in the other direction. And since they're the same quantity, it cancels out. So therefore, V3 is equal to 0 due to Ohm's law. And so Vx, V2 is equal to 0. And that is the answer. I put this in SPICE, and this concurs with SPICE. Time for the I1 circuit. But so far, we have 2 0 contributions in a row. So if you're like sitting in the exam room and this is what you got, you would probably be feeling very nervous. And you should, because that's not normal. So if I draw the circuit, so here's our circuit. We know the whole shindig. So it's like we have the voltage of X due to I1. And we want to see if, I1, how much I1 is contributing to Vx. And that's all we're doing. The dependent source is like a control that like manipulates how we're going to do the algebra to get what we would need. So now we have a ground here. And so effectively what that means that this part of the circuit right here is just kind of just ignored. We don't really care about it. So I redrew the circuit and I'm like, okay, good. So what's going on here? Well, we could say the current going through R4 is, call it I4. And if we do KCL, we know that I1 plus Vx due to I1 over R3 is equal to I4. So these currents are like going in here, and the current's coming out. And this makes sense because we're assuming that the potential here is higher than the potential there. So if I do KVL, like KVL around this loop right here, what I would get is, I would get this. We know what I4 is, so we can just plug this guy into there. And what would be is this. It would just be that. So doing some algebra, I'm going to go ahead and skip to this step. I don't know if this is exactly what you're going to get, like this expression, but this should simplify to minus 3 volts. So therefore we can say Vx I1 is equal to minus 3 volts. Boom, 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 boom. So you could go from here to here. So now for one point, the final point, what's the voltage across Vx? And include the polarity. Well, all we have to write is this. Vx is equal to Vx due to V1 plus Vx due to V2 plus Vx due to I1. And we know that's 0 and that's 0 and that's negative 3. So it would just be negative 3 volts. And that's it. One of the things that's important to realize is that this problem is like kind of like a time sink. It's non-intuitive because you would think the other two sources, V1 and V2, would contribute something, but apparently they don't. And I've tested it in SPICE, they don't. This question is very tricky. It's designed to like make you have self-doubt about what's going on. And it's unforgiving because like it's taken a little while to solve this problem. It's like you have to be very quick and you can't waste time. So if you were to go back to V1 and V2 circuits, you would see that looking at this right here, you can just find that relationship, which is this relationship right here. And then you can immediately tell that they should be contributing nothing. So if you could actually see that and do that real quick, this problem should not take more than like 10 minutes. Because like you spend like 2 minutes figuring out, oh, that's what's happening here. And then then you would spend the rest of the time just solving for the last circuit. So like if you could see that from right away, like this problem actually is not that long. But if you want to make sure, yeah, it's going to be a little bit longer. when you're doing dependent sources, all you're finding out is that how can we group together the dependent part of the source? How can we group them together and make them equal some constant? And in this case, that constant is I1. So it's like these terms are in some combination equivalent to I1, which is a constant. So you can you use algebra to find what Vx actually is. When you are boiling down to it, that's what dependent sources are trying to accomplish. So fundamentally, it's not that hard of a problem. Here's my Thevenin video if you need some tips. If you liked it, leave a comment. I'd like to know your thoughts. Thank you for watching. Good night. Sleep tight. Don't let the bedbugs bite. I'll see you guys later. Good night.